Hello, everybody. I'm Jonathan Garzan, Head of Product Management at Apstra, and I'd like to welcome you to today's webinar titled Intent-Based Analytics, Prevent Network Outages and Grave Failures. In this webinar, we'll introduce an exciting core component of our recent AOS 2.1 release, Intent-Based Analytics, or IBA, and demonstrate how our multi-vendor software provides your data center the agility you require and lowers your costs. Our featured speaker today is Josh Sull, Solutions Architect at Apstra. Hey, Josh.
Hi, Jonathan.
Josh is going to give an overview of how network operators, can easily configure AOS to quickly detect and prevent a wide range of SLA violations. He will then take you through a real-life scenario demo. As always, we'll answer your questions at the end of the presentation, so please enter them below the presentation screen at any point in time. Our presentation today will be about 30 to 40 minutes depending on questions. So with that, let's get started. Josh, the floor is yours.
Thanks, Jonathan. So today we're going to talk about some exciting new features in AOS that are available with our 2.1 GA release. For some of our newer guests, Apstra develops an application called the Apstra Operating System, or AOS, which takes high-level business logic and requirements, which we refer to as intent, and translates that into a fully running data center network environment with tools and workflows specific to the desires of the administrator. We create an abstraction from the underlying hardware that enables you to interact with the network as one logical system. The goal is to move from the legacy management standard of configuring devices on a box-by-box basis and monitoring them with a separate isolated tool. Is it possible for us to start operating the network as a single unit, but retain the freedom to pick our own hardware and architecture? Networks have always been distributed systems with the primary goal of eliminating single points of failure or shared fate scenarios. So at Apstra, we are focused on building tools for the consumption of network services with that mindset. This single system, in our case today, a leaf-spine IP fabric, has a central goal or set of services it provides to the business. We describe this as intent. AOS is driven by intent and supports multiple vendor equipment to interoperate in a coordinated manner to achieve these goals. It is also what we describe as a closed loop, meaning the operating conditions or network state is fed back into the platform instead of being collected by a separate system. This is akin to how a self-driving car ensures it is driving within the lanes on a highway, or how a thermostat can determine if it needs to heat or cool a room to reach the desired temperature. AOS has a centralized, highly scalable data store that contains the state of the system and compares it against the intent. It issues alerts or anomalies when there are deviations. It can also be used to autocorrect or self-heal when an event occurs. These rules and conditions are automatically created based on the reference design you select, but the operator is free to create their own set of logic that defines this behavior. Unlike automation and telemetry tools from the individual vendors, AOS can manage many different network operating systems. It doesn't replace these NOSes. It just knows the proper way to configure each device type according to industry best practices as if it was a trained expert. Today, the big feature we're going to be talking about is intent-based analytics, which is a new feature enabled in 2.1 and is currently shipping to customers. These analytic capabilities have been part of AOS since first release, but we're now exposing this feature for customers to leverage. This is where we think network experts will be able to apply their custom troubleshooting and best practices and maximize their value to the organization. We're providing several complex checks to get customers up and running with IBA immediately. You may have heard recent announcements about IBA or assurance functionality from a large vendor, and we're proud of the fact that our vision is being validated by the largest names in the industry. Unlike other solutions, our platform is multi-vendor and hardware independent, so IBA works across all systems without the operator needing to know the differences between the specific syntax of commands, output, or operating guidelines. Everything is normalized, so you can simply interact with the data in a meaningful and visual manner. IBA is not a legacy network management system, or NMS. It is a totally new way of operating your network. So how is this different from what people are doing now? Well, the status quo for the last 10 years is that we've either been graced with or subjected to a mountain of incoming data from our systems. The amount of data you can collect is greater than ever before, but it often seems like you need 10 screens to make sense of it all. If big data helps you find a needle in a haystack, Then IBA helps you find and assemble many pieces of a single needle from several haystacks. A smart engineer generally looks at many screens and visuals and is able to analyze the problem in their brain. So IBA gives you the tools to put these capabilities directly into the system. So we have lots of tools and ways of visualizing the data, but very little intelligence about what it means or what is important at a given moment in time. How do we know if traffic spikes are part of a daily server backup and not a malfunctioning application? What is normal? Can we apply mathematical functions to make things simpler to understand? Perhaps most importantly, can we correlate information from multiple sources in an intelligent and self-updating fashion? We don't want to reconfigure the monitoring platform every time we make a change. If we add a new switch, the system should automatically detect it and start monitoring it. Better yet, the system should know what purpose that device is serving so that telemetry is fine-tuned to that specific purpose. Most network operators are taking data from their systems and assembling this application stack themselves. First, they need to collect the data, which is hard to do when you have multiple vendors. They need to normalize the data so the sets are all consistent. Then they need to determine what to do with all of it. It takes a long time to get this all to work right, and making small changes to the network can break the system. All of this logic is sequential and manually defined. The operator is responsible for figuring out all of this and keeping it up to date. So how many of you have built a network and left a single task at the end of the project that says, add to monitoring tools? We're not just talking about adding a new management IP address to MRTG. We need a system that interprets the addition of the new device to make adjustments in all sorts of ways. So actually, the process looks something like this. A huge number of disconnected systems and tools with no correlation. Different formats, racks of appliances or computer resources, phone calls, etc. Many companies have assembled their own stack of tools or software to attempt to do this. But as most of you know, these heavy stacks are very fragile and are really never as simple as we want. So what is intent-based analytics really? We're going to logically link the intent of the system to the desired operating parameters. We want to do this in a very generic and vendor-agnostic fashion, so the tool will automatically update itself. If I define some normal behavior for my spine switches, I want to know that every time I add a spine that the system knows how to monitor it and what the addition of that device means to the rest of the network. We also want to create baselines that support statistical analysis with the ability to watermark the normal behavior of the system. Any change to the design or policy of the system should update the analytics and expectations for the desired running state. And lastly, it would be great if we did not have to watch a screen waiting for a spike. The system should simply tell us if a condition or set of multiple conditions is being violated. So we start this journey with the AOS data store, which contains all of the normalized data for devices we're managing. Most engineers think that their network looks like the diagram on the left, and to a certain extent it does. But if you consider all of the interrelated and interconnected parts, it's actually the graph diagram on the right. With AOS, you don't need to do anything to gather this data. AOS is already taking care of the heavy lifting. We can just ask questions of the network with a simple query. For example, let's ask the network a question with our real-time API Explorer. We have autocomplete and suggestions, so you don't need a map of the schema in order to make this all work. I want to ask a complex question. Give me all fabric interfaces where fabric interfaces mean those facing spines and not facing servers or external routers. On all leafs running OS version XYZ, because it may have a bug that we're concerned about. The live query below returns a dynamic set of interfaces matching this criteria. Remember, the query runs against our statement of intent. So adding or changing the system will provide different results for the query without us having to do anything. I can change my architecture, I can add new routing policies, create VLANs or VXLANs. All of these changes to intent can automatically update our analytics, and the system-wide validation is still functional and in sync with the actual state of the network. Once I create the query I want, I can also define what is normal and what is unexpected. And finally, what I want to do when this condition is met. I combine all of this in a single REST call to the AOS server, or build it in our GUI to activate the check. And AOS will then run these checks at the defined interval until instructed to stop. It will automatically update itself if there are changes to the network. This is the equivalent of the mental model we discussed, but now it's in code in AOS and running all the time. So this right there has shortened our work process by months. IBA starts from the intent in the data store. Each building block is what we call a pipeline. Pipelines are mathematical constructs that define how data is processed to reach a particular actionable insight. IBA probes can contain multiple pipelines. You might only want to be notified if multiple pipelines are indicating an SLA violation. This would help to cut down on false positives and also minimize the number of alerts sent to the NOC or operations team. This is not just simple watermarking, it's a multi-dimensional decision tree. And you can customize just about every bit of logic. You can even combine data from elements of your network that were previously unrelatable. So an example of a probe might look like this. You can tolerate a certain amount of packet loss, or interfaces bouncing every now and then, or even routing flaps. The network is highly redundant, and ECMP load balancing ensures that there are multiple paths between hosts. But if two of these three conditions are occurring at the same time, that's concerning. It would typically require some action by the operator. So each one of these conditions can violate their SLA at any time, but not more than one of them at any time. If that occurs, then we're going to issue an alert or ideally take a predefined action. So we have a team of experts at Apstra in our Advanced Solutions group who help customers build some of the more sophisticated probes. We're making these system checks available for download on GitHub today. And here's a sample of what you'll find in the public repository. IBA includes the ability to define custom visualizations for each stage of your probe. These are included in AOS, and you simply need to pick which view you want as you build the pipeline. You can also stream the output of each stage in a probe to an external collector for storage or analysis. Now, in order to get better insights, we want to apply some analysis to the data as it flows through the processors. We can define a range for the baseline. This permits the operator to tune in to conditions that they may wish to alert on. We might be interested in looking at the amount of traffic flowing across a number of related links in our network. The selection of links is done via our Graph Explorer. We can determine a baseline over a period of time and alert when the traffic spikes above our reasonable expectations. So in this case, we're watching the number of gigabits per second flowing across these links. If a spike causes a monitored group to go above or below the delta, we can be alerted or take some corrected action. We can also use some dynamic analysis to look for deviations from the patterns. First of all, we can rule out areas or segments of the data based on known conditions. In this case, we expect some traffic spikes after 5 p.m. because that's when business permits application owners to do large file copies or snapshots. So let's not alert the NOC every day when that happens. That's a pretty simple bit of business knowledge that we can insert into every processor. Another good example is that we want to be alerted to a sudden increase in the number of learned MAC addresses, as this might indicate an application error or switch problem. But more likely than not, the culprit would be at 9 a.m. when everyone turns on their computers, phones, etc. So we could tolerate a standard deviation of 3 sigma from 8:30 a.m. to 9:30 a.m. But we want to be alerted if there's anything above 2 sigma during the rest of the day. I think this is a rather basic example, but it shows the power of IBA, specifically that you can put your intent directly into the analytics. Also, more importantly, we can support this dynamic analysis using standard deviation in this particular case. Since we're free from tying this probe to a hard number, the system is very flexible and can be rather intelligent about how it issues alerts. The standard deviation of measured traffic is not tied to the number of links in our leaf spine design. So if we were doing maintenance during the day and the number of links decreased when a device was offline, the system will not issue false alerts. AOS will already know about the devices being out of service. The graph query will return a lower number of available links, and we won't have any false positives when we're doing our normal maintenance. All of this is system-wide. Unlike traditional methods, the addition or removal of devices is handled automatically. So now I've shown you some basic and complex examples of how IBA can save you a lot of time running your network. I didn't even mention the improvement in quality of life for the operator, but I digress. So let's jump over to my demo environment and we'll take a quick look at a couple of probes I've configured. Here you can see I'm logged into the AOS server and I'm viewing the dashboard for a leaf spine system. Everything is green, so I have some assurances that the network is physically up with no major problems. You can see the high-level service monitors for our IP fabric, external routing, L2 server connectivity, and more are all shown here. And I bet a lot of people on the call have experience with everything being green, but there's still being some underlying performance issue in our network. I can click on this new Analytics tab in order to view the currently configured IBA probes for the network. Let's go ahead and do that. Now, each network can have its own set of probes, and obviously, the probes for each system can be different, so I can assign different SLAs to the various areas of my network. I have two probes I've created in the system, headroom and fabric MLAG imbalance. These are two very common scenarios that IBA can mitigate, and these probes are two of the ones available in our GitHub repo. The headroom probe is specifically designed to watch for traffic flows between rack 1 and rack 2 in that system. Maybe rack 2 has my vSAN, and I'm used to seeing a lot of bandwidth going to that rack from the message bus servers in rack 1. Probes are composed of the processing stages that I mentioned before. I attached a visualization to one of the stages here. This visual shows a server in rack 1 on the left and a server in rack 2 on the right. These two hosts are connected by 4 top-of-rack leaves and 2 spines. So this is a standard clause designed to maximize my ECMP load balancing. And therein lies the problem. ECMP may possibly hash TCP sessions onto one path, and they'll stay on that path for the lifetime of the session. If that traffic is massive, we'd call these elephant flows. They might step on the smaller real-time application or voice flows that are referred to as mice. So I want to view when this is happening, as we can simply reroute or pause the large flows to get them off the wrong path. I can hover over each path to see how much bandwidth is currently being consumed in real time. This is a demo environment, so I don't have a bunch of elephants running around, but you get my point. You could quickly look at which links are yellow or red and then know where the bottleneck is. AOS isn't doing anything about this problem, as it may be a normal condition that you might just want to know about. But we can attach an alert or action to the probe to resolve the issue. Now, I can also view some of this information in a tabular format. For all the links that make up this part of the fabric here in this separate section of the probe, AOS is populating this table directly from intent. So if a switch was offline, those paths would simply not appear in the list at all. AOS knows all of the available active ECMP routes, and it shows me how much traffic is on each one. It's also normalizing the data formats and metadata to eliminate differences between how vendors report the traffic load. So now let's jump over to the MLAG imbalance probe, which has a lot more stages. First, let me show you how I'm going to collect the data that I'm interested in. Right here on the right is the graph query I created and set as a source for this processor. I can copy the query and jump over to my Graph Explorer. This is a little bit backwards. You would typically craft the query in the Explorer and add it to the probe, but I want to show you what sort of data I'm feeding into the pipeline. If I paste the content in here, I can see the output that I'm interested in. So this is the definition of the data I want to put through the processor, and when I click on play, I get a real-time answer. The IBA probe is using this question to generate the data fed into the processor in real time. It's all JSON format, so you can easily decipher what it is that you're looking at. Let's jump back over to the probe itself. On the left, you can see which stages feed into other stages. So you can conceptualize the temporal and spatial design of the probe. The output of each stage is fed into a different stage, as indicated by the arrows on the left. Each stage can have its own visualization. So in some cases, it makes sense to see real-time data, and in other cases, it might make sense to see a time series view. As I work my way through the stages, I'm transforming the data into something that makes sense to me. For example, I want to use the percentage of traffic flowing from one host to the 2 Tor switches running MLAG, and apply a standard deviation calculation to that number, to possibly generate an alert or anomaly for the operator. The actions, in this case the alert, will be shown down here on the left as a red icon. I can issue an alert in any stage, or I can assemble multiple bits of data before notifying the NOC. So I can walk through the logical processing of the data to figure out how and when an alert will be generated. If you can't see the details, don't worry. Everything in this particular probe is available for free in our GitHub IBA repo. So down here is where the alert will be issued. You can see that the value for this particular stage is true. And of course, this means that the alert is being sent in real time. So those were the two probes I'm going to demonstrate today. So that was a very quick intro to the power of IBA probes. We're going to be talking a lot more about probes in a future webinar session, so stay tuned for that announcement. We built IBA into AOS from the very beginning when we started developing the software about 4 years ago. Since that time, we became the chief consumers of its capabilities to augment our reference design and integrated monitoring. We've been talking about IBA publicly for 4 months now, and we're so excited to finally be able to give it to our customers. This is game-changing technology. We truly feel that operators who use IBA will dramatically improve the performance of their networks, and more likely, it'll free them up to work on challenging problems specific to the business, rather than chase down the routine and stressful network outages. So I hope we've given you a good glimpse of the future of networking, and we're looking forward to talking with you again soon about further enhancements to IBA. At this time, we'd like to take a few questions from the audience. Jonathan?
Yes, Josh, thank you very much. It was great. We already have a few questions from the audience. Actually, we have a lot of questions about Cisco and their recent announcement. But I'd like to start with a few IBA specific questions. Okay, and let me start with this one. Can you programmatically configure probes? Josh, do you want to take this?
Yeah, great question. We can create probes with a single REST API call. So you could define your query and the various conditions, that you want a certain standard deviation, say 3 for X number of minutes on this particular value, and you want to be alerted in a certain fashion. And all of that is a single REST call into AOS. And once you've done that, that probe is active in the system until it's turned off. So you don't need to update it, and you don't need to check to make sure it's running. It's in there for good. All
right. Can IBA integrate with my existing alerting system? I can take that, and you can add if you want. But yes, any telemetry or anomaly, which are deviation from intent that we have in AOS, can be streamed to an external system using Google Protocol Buffer. And you can use that to integrate with any third-party analysis for this data. And we also have, as part of our community code on github.com/Apstra, a set of integration with Prometheus and InfluxDB. These are time series database with CAN dashboards, Grafana dashboards that we integrate through some Telegraph plugin. So it's very easy for to actually integrate with the external devices, external systems. What hardware do you support? That's a recurring question. So that we support the variety, a lot of different vendors. That's actually part of the core value of AOS. And we have validated our reference design on Arista, Cisco, Dell, Mellanox, other vendors, including Whitebox running Cumulus Linux. And we are customer driven and can quickly add others. What I can take this one. Can IBA probes be chained together? And actually, I have a related question that is, what is a key advantage versus a non-intent-based strong analytics correlation platform working on the same data? I think I'm going to take those two at the same time. So can IBA probes be chained together? And how does that relate to the advantage that we provide? So absolutely, IBA probes can be chained together. It's actually a key capability. You already know that IBA probes themselves describe how the different data processing stages are chained together to extract insight from raw telemetry. Now, as the question asked, you can also write IBA probes that rely on the results of other probes. And effectively, you can compound the results of multiple analysis on what seemed to be unrelated in the past into new insights. And that's what Microsoft research team calls multi-dimensional health monitoring in its white paper on gray failure. And there is a recent blog from our CTO, Sasha Radkovic, on this very topic that you can look up on our website, apstra.com. What is the scale of IBA? Question about scale. So first, AOS is built on top of our distributed data store, which is horizontally scalable, and it can scale to hundreds of thousands of managed devices. Now, each particular probe has its specific memory and CPU footprint, which really depends on how you configure it. The element of a probe are processors, as we described, and we can run hundreds of thousands of these processors on a single AOS instance. And for further qualification, we have a team of experts, our advanced service engineering team, that can not only help you build those probes, but also assess the footprint of your specific probes and size the AOS deployment accordingly. Actually, let me now address the few Cisco-related questions and take this question: how does AOS compare to Cisco NAE? That stands for Network Assurance Engine. And so the answer is that unlike Cisco NAE, which requires an integration with ACI or titration or both, IBA is an integral component of AOS. As Josh mentioned, that was part of AOS initial continuous intent validation from day one, and we're now exposing it to customers for injecting their own reasoning about what's happening in the network. And AOS provides a complete network lifecycle management from design through build, deploy, and operate phases. So you don't need to install and integrate multiple products to get continuous validation of your intent. AOS has been built from the ground up to do that, to do exactly that. Now, in addition to that, AOS is also multi-vendor and allows you to choose the actual hardware that better suits you technically or commercially without having to change your operational model, which is a great advantage. Okay, that seems to be it. So this concludes this webinar. You've heard a lot recently about the requirement to simplify your data center network to ensure the success of your digital transformation. Please look through the materials on our website and request a one-on-one demo at www.apstra.com, and we can walk you through how to get started. If there's any question that is unanswered, we'll answer them and reach out to you directly. Please also rate this webinar and send us feedback so we can improve future ones. Thank you all again for attending today. We look forward to hearing from you and to seeing you on our next webinar. Thank you. Have a great day.